which is relevant, but I'm not going to talk about it. Yeah, what I want to develop is this idea of a complexity geometry, and especially of the idea that the complexity geometry is a geometry of either state space or the space of unitary operators. And on that geometry, a system evolves. If the system is chaotic, we might expect the evolution on this complexity geometry also to be chaotic. But the motion in this geometry is classical. It represents the evolution of a point in Hilbert space. It's a classical geometry. That's to say it's a classical evolution. And as far as I can tell, for a good complex system, a generic quantum system, which is not integrable, the motion on this complexity space is chaotic, and I think represents what really should be called quantum chaos. Quantum chaos right now seems to be associated with the phenomenon of scrambling. Scrambling tells us that there's a Lyapunov exponent, and the Lyapunov exponent governs, what does it govern? It governs something called size of an operator for a relatively small amount of time. How long a time? Roughly the scrambling time. Scrambling time is a short time. Okay? It's a logarithmic number of qubits of the system. It's a short time. And the real interest in chaos really has to do with long times, or much longer times than that. The idea of a butterfly effect, of course, does entail the idea that that trajectories do separate, and that they separate exponentially. But it's really telling you that if you wait a long time and you try to reverse a system, the longer you wait, the more delicate it is to reverse a system without making a mistake. If you take a movie of a system of molecules, classical molecules, for example, and you run it for a short amount of time, and then you run the movie backward, perhaps with a tiny, tiny error, the system will come back to what it was, do something close. But if you wait a long time, and the longer the time, the worse it gets, the same tiny error will very, very quickly destroy the possibility of returning the system to what originally was. That's, of course, among other things, the origin of the second law of thermodynamics. And I think the most interesting aspect of chaos is the long-time behavior of chaos, the long-time behavior. Maybe not exponentially, maybe not recurrence times, but times moderately long where you can see that the instability of the system just makes things worse and worse and worse for the possibility of running the system backward. So I think, in a sense, the scrambling aspect of it is the short-time behavior, which does tell you that things separate. But how do you think about the long-time behavior? And I think the right way to think about the long-time behavior is through complexity. And what it says is if you start a system or run it in two slightly different ways over long periods of time, the relative complexity of the evolutions just gets larger and larger and larger. And that is what we would like to see in a geometric way in terms of some sort of geometry of the evolution of states. Of course, in classical physics, it's just phase points separate. Just phase space is the thing we look at. In quantum mechanics, it's not quite clear, because if you use the ordinary measure of distance on Hilbert space, well, the ordinary distance on Hilbert space just maxes out at pi over 2 or something. Or the same thing for unitary operators. The ordinary inner product metric simply gets maximum once the vectors become orthogonal, or the unitary matrices become orthogonal, and it's incapable of describing this situation where things continue to grow and grow and grow in relative complexity. And so that's the reason for introducing a new kind of geometry, the Hilbert space. We've discussed that. And today I want to get into a bit of the details of what we do know about complexity geometries. The idea of a complexity geometry was invented by Michael Nielsen. How long ago? I think the first paper I read on it was from around 2007. I didn't read it in 2007. I didn't know about it in 2007. But in fact, I'm not even sure I knew what the word complexity meant in 2007. I don't think it's here.
2006. 2006.
2006. I think the paper I read was from 2007. This is the one with Dowling and that's 2006?
Yes.
2006. They were early.
In the archive or in the
Yeah, I'm checking the archive.
Submitted or accepted?
Yeah. Okay. And so we'll talk about it a little bit. I'll tell you what the limitations are of what Nielsen proposed and possibly how to fix it. The other aspect of things is once you have this dynamical, I always call it an auxiliary system, just the motion of the state vector. Once you have it formulated as a dynamical system, you can think about doing statistical mechanics on it. And as I said last time, do averages of classes of problems involving complexity that might be much too hard to do for individual instances, and get a statistical period of complexity.
Question?
Yeah.
So think about statistical mechanics to define the entropy. Normally we think of the volume of phase space in some units, which normally we think of h bar. So is there some analog of h bar in this space? Or?
No, okay. Imagine you're really doing classical physics, where there is no unit. What do you do about it? Remember, entropy was invented before quantum mechanics.
But it was some random unit.
Coarse graining or something.
You introduce a little coarse graining, and then you say, does anything depend on the coarse graining? And it doesn't. Entropy differences don't depend on the coarse graining. It's just that little coarse graining enters in basically as an additive constant.
But the coarse graining is normally done in a particular metric, and that will matter.
Yeah, I mean there is no natural metric on phase space.
But the coarse graining kind of gives you one in some sense.
Well, the coarse graining gives you one, but in view of the fact that entropy differences don't depend on the coarse graining, it really drops out.
Well,
you could make crazy coarse grainings.
yeah.
You could make crazy coarse grainings, and where the coarse graining involves little shapes which do all kinds of crazy things.
I guess I just don't know what crazy is until I have an idea of metric.
That's right, you don't have an idea what crazy means until, that's correct. I think the analog of that in quantum mechanics may just be you don't have an idea of what crazy means until you have a notion of k-locality, until you have a notion of locality. I think that's probably what it is. But it is true, the idea of a coarse-grained cell is not canonically invariant. The idea of k-local is not unitarily invariant, so I suspect they're related, but I haven't thought about it a great deal. Classically, the entropy, strictly speaking, is always infinite as you let the coarse graining go to zero. And quantum mechanically, I think the notion of complexity is also always infinite until you do some coarse graining. And the nature of the dependence on the cutoff is the same. Logarithmic dependence on cutoff. So, good. We'll get to that. Not today. Okay, so what we discovered last time, or I know from Nielsen, in fact, is the geometry of relative complexity. Relative complexity thought of as a metric has the property of being right invariant and not left invariant. Incidentally, there's lots of stuff out there, even on the internet. Very nice article by a mathematician from IAS named Milner on these kind of metrics. But just be careful, when you look it up, don't look up right invariant metric, you won't find anything. Look up left invariant metric. Okay. All right, so right invariant metric. Let me just review very, very quickly what we said. I'll be interested, there's a whole bunch of different kinds of complexities. Look, there's an infinite number of different kinds of complexities, but there are different types of general broad classes of complexity. One of them is the complexity of states. Then this can be either quantum mechanics or classical mechanics. The other is complexity of what in the quantum mechanical case becomes unitary operators, what in the classical case would be permutations of states. Permutations of states are the analog of unitary operators. So there's the quantum versus classical separation. There's the state versus functions of states, which means either unitary operators or permutations, depending on whether you're classical or quantum mechanical. And then there is computational complexity, which is what we've been talking about. I'll tell you in a minute what these mean. Versus algorithmic or Kolmogorov complexity. Computational complexity is simply the question: how many simple steps does it take to go from A to B? If you have a natural notion of simplicity, for example, a unit operator as a unitary operator is the simplest unitary operator, I claim. You can question that, but most of us would agree the unit operator is the simplest. So how many simple steps, gates, does it take to go from 1 to U? In classical physics, if we were talking about, not classical dynamics, but perhaps a classical automaton. I want to be talking about bits, computers. Given a simple configuration, could mean all bits in the zero state. Okay. How many fundamental simple operations does it take to go to an arbitrary configuration of those bits? And that's pretty small. It's never bigger than the number of bits. It's just what's the maximum number you have to flip. State complexity, either classically or quantum mechanically, is usually its maximum is usually exponential. And as I said, computational complexity means how many steps do you have to take in order to get from A to B, or from simple to whatever it is. Algorithmic complexity is a different concept. If you think of computational complexity for how long does a computer have to run in order to accomplish a task, algorithmic complexity has to do with how complicated the program that you're going to run is. How long, in terms of basic steps of writing a computer program, how many bits does it take to write the computer program that you're going to run? So algorithmic complexity has to do with the complexity of your algorithm. Computational complexity has to do with how long does it run before it achieves its goal. And both will be interesting to us. But of course, main interest today is computational complexity of unitary operators in quantum mechanics. So that's what we're interested in. And we're interested in the evolution of a unitary operator. Let me just very quickly review.
Leonard, can I ask you a question?
Yeah, sure.
Where does algorithmic complexity enter into the story here? I mean, there's no
Okay.
computer running an algorithm if it's a black hole.
Yeah, that's right. But there is a rule for evolution, and that rule is called the Hamiltonian.
Okay.
So how complicated is it to write down what the Hamiltonian is? Typically, it's not very complicated normally. Let me pursue it just a bit. How many bits does it take to say n equals force of a conformal field theory?
That many? Maybe the log of that many?
No, well, yeah, but the log of that many. So it's not many. Okay, good. So typically then the algorithmic complexity of specifying a Hamiltonian is usually small, but you can imagine Hamiltonians which are just very difficult to explain to somebody.
62-0 theory?
Yeah, well, I don't know.
World volume theory.
That's what. We could make up some really weird Hamiltonians, okay? And it might take many lines of computer code even to explain what they
I
are.
mean, especially if they are time dependent, right?
Hmm?
Time dependent, if they are time dependent, if they are even.
Oh, and if they're time, good, that's even worse, right? So, supposing we're talking about computer programs, here's a kind of computer program, or a circuit. And a quantum circuit, we consider the class of quantum circuits which consist of relatively shallow, that means short circuits repeated, one after another. You can make some pretty complicated outputs by taking a relatively simple short circuit and repeating itself over and over. And in that case, you would say the algorithmic complexity is how many bits does it take to specify the thing that you're going to repeat over and over. You don't have to specify the whole thing, you just have to specify the depth of the thing that you're going to repeat. That's like specifying the Hamiltonian. On the other hand, if you had a random circuit, a Brownian circuit, then at every step you would have to re-specify, and the algorithmic complexity would be very much bigger. So for time dependent, we can imagine the algorithmic complexity being as large as the computational complexity. That would essentially mean a fully random Hamiltonian, or fully random Brownian circuit. Okay.
Well, I mean, I guess if it's fully random, you could have at each layer a random generator, and then you can write it very compactly, right?
Yeah, that sounds pretty
So, yeah.
simple. Every time we need to apply a new circuit, pull a Gaussian, pull something out of a Gaussian.
But that actually it's actually describing the thing you don't want information. Describes statistics.
No, that doesn't, that describes a class of things, an ensemble of things. Oh, you see, I don't think that counts.
Okay.
I don't think no, I think you have to specify what it is, not just a probability for what it is.
That's what you meant, right?
Yeah.
All right, the place where algorithmic complexity mathematically comes up is in specifying strings, not superstrings. Strings of bits. Given a string of bits, how complex is it? How difficult is it to say what that string is? If I give you the string 1, 1, 1, 1, 1, 1, okay, that's easy to specify. All ones. It takes 2 bits or some number of bits. The maximally algorithmically complex strings, you can always specify a string by saying what it is. Just writing down all the bits. So the maximal algorithmic complexity is simply the number of bits. When the algorithmic complexity is the number of bits, that is really called a truly random string. Now, it only makes sense in the limit of large n, but that's okay. So this is not the subject for today. It'll come back though. Okay, let me just very quickly remind you, our equation of motion is IU dot is equal to HU. H is assumed to be some sort of sum, some sort of k-local sum, which involves a set of coefficients, J, I won't write it down exactly, and a collection of qubit operators. If we're in SYK, these are fermionic. If we're in spin chains, these would be spin operators. And for example, for a k-local or for a 2-local Hamiltonian, this would just involve components of the spin of the ith qubit with the jth qubit with a bunch of coefficients or a bunch of coupling constants, J. And typically we'll be interested in trying to answer questions by averaging over an ensemble of J's, as in SYK. Very good strategy. Okay, but for the moment, the J's are just numbers. We can also write this as a sum of, I'll call it J sub I, sigma sub I, where sigma sub I doesn't represent the component of any particular Pauli matrix. It represents all the possible elements of the Pauli algebra, which can mean single qubit operators, 2 qubit operators, 3 qubit operators. And the number of fundamental Paulis that go in here is called the weight of the operator. So if I take 1 qubit operators, those have weight 1, 2 qubit operators have weight 2, and so forth. And for a k-local operator, we would say, well, we're going to sum over all I such that W of I, the weight of the operator I, is, let's say, less than or equal to some little k, where k is the degree of k-locality. There's just a notation to use capital I just to label all 4 to the n minus 1 Pauli, elements of the Pauli algebra. Okay, so this is our equation. Here's our Hamiltonian. I showed you a trick last time where you differentiate this twice. You double dot, that's h u dot, and then solve the first equation here for h by multiplying through on the left by u dagger, on the right, sorry, by u dagger. You're going to have h, and so we have I u double dot is equal to u dot, u dagger, u dot, or like so. And now this becomes a second order differential equation, like Newton, F equals ma, with a acceleration term, a velocity dependent force term, but no memory of what h is. Where does h come in? H comes in the initial conditions. This is a motion, of course, on a unitary group. So here's the unitary group. We start at the origin, which means the unitary operator, and we evolve. And where did h go? H went into the initial velocity. It's easy to prove that the j's, so j sub I, is simply equal to the initial velocity, let's call it initial velocity, along the direction of I. The direction of I is specified by a particular direction in the space of generators away from the origin here. So the velocities are basically the j's, the initial velocities. The initial velocities of j are j. And if we then had a initial probabilistic distribution of starting values of u, which might be concentrated all at u equals 1, I'll allow that. Everybody concentrated at u equals 1, but with a statistical distribution of Hamiltonians, that would correspond to a mechanical or a statistical mechanical problem, not an equilibrium problem far out of equilibrium, but with a statistical distribution of velocities in the beginning and all particles start at the center. So that is basically the connection with classical dynamics. Incidentally, one other thing, if the couplings here are distributed Gaussianly, as again as they would be in SYK, then that would correspond to a Maxwell-Boltzmann distribution of velocities. Okay. Now we can represent this motion by a Lagrangian. It's a canonical system, and the action is very simple. Oh, yeah, this equation is the equation of motion for geodesic on the group space. And the action for the motion of a geodesic on any space, on any Riemannian space, If we coordinatize the space by a collection of coordinates, and now I'll call it xm. M and I and j are different things. This is just a collection of coordinates representing space. It could be the components of u, but any collection of ordinary Riemannian coordinates. Then we can use either a first order action to represent the motion of a system or a second order action. The first order action, of course, is just geodesic length on the space. And the second order action, also, if you impose a constraint, namely you specify the value of the energy associated with this is not finished, let me just finish it, GMN. This is the metric, and the action in the first order is just to take the square root of this times the tau. The second order action is just to use this thing by itself as a Lagrangian, but then you have to supplement it with another constraint. The other constraint can just be to constrain the value of the kinetic energy, but we'll come to that. All right, and the idea of Nielsen was to use such a geometry, not this particular one, to use an appropriate metric in place of this, well, perhaps of this form, an appropriate metric so that distance measured on the unitary space would become relative complexity, would measure the complexity of going from one point to another. So this was Nielsen's idea.
What do you mean a metric not of that form? That's kind of.
No, I didn't even write a metric.
Okay, yeah.
I got ahead of myself.
Okay.
Right, yeah. Okay, good. Okay, so let's now talk about metrics. There's the ordinary, I think I can erase this. We have this. The ordinary metric on SUN, or SU2 to the n, incidentally, I will sometimes call the number of qubits k, and I will sometimes call it n. The reason in our paper that we wrote on the subject, we called it k. But then too many things got to be called k. Little k, big K, there were several different k's. So in talking about it, I tend to use n for the number of qubits, but I sometimes forget and use k. So just remember, k equals n. Except when it doesn't. All right. Okay, so let me call it the standard metric on the unitary group is just given by, what is it? Cosine of the distance between 2 points is equal, let's say the 2 points are u and v, two unitary operators on the space, is what? Trace of u dagger v? I think I have that right. Yes, let's just check that. If v is equal to u, the trace of one, and the other convention I will use, this convention, and trace of the unit matrix is 1. Trace of 1 equals 1. In other words, it's a normalized trace. I just don't feel like writing 2 to the ends of the denominator of the formulas. So my use of trace will always mean the normalized trace. So let's see, so trace of u dagger u, which is trace of 1 is 1, and that means d equals 0, right? Okay. And I think the biggest value d can be is pi over 2. If u dagger v, trace of u dagger v is 0, in other words, if u dagger and v are orthogonal to each other, that's as far apart as you can get, then d is pi over 2. So this unitary group is sort of very compact. The largest distance between any 2 points is pi over 2, but certainly that doesn't reflect what we want to reflect, namely that the relative complexity of things can get very large. So this is not what we want, but nevertheless, the metric, this metric, which is Does it have a name? Does anybody know what it's called?
This.
I'll just call it the standard metric, or the inner product metric. Okay, it can be written as in the form dl squared metric on this space is just 1/2, no half, trace of u dagger dot, well, sorry, trace of du dagger du.
Sorry, do you need an absolute value behind it?
Yes.
So, trace.
Where does the absolute?
Outside
value?
the trace, yeah.
Yeah, very good. Yes. Good. I don't think I need it here. dl squared is just trace of u dagger, of du dagger, du. If I wanted an action for the motion of a particle on this space, on a motion of a particle which executes a geodesic, I would just write du tau, du tau. I put a half here just because of the standard reason we always put a halves in action, and then I would integrate it over the tau. This is not dl squared anymore, this is some action. And then with this action here, the coordinates being the components of the unitary matrix, the motion would generate geodesics. Okay, but this is a left and right invariant metric. Let's put it back as a metric, not as a action. Trace. If I multiply from the right with a matrix, on the conjugate side I have to multiply from the left. Taking the trace will cancel out the v and v dagger here. And so it's right invariant, and it's also left invariant because any v and v dagger I put in here will also cancel out. So this metric is completely left and right invariant. It's called bi-invariant. It's not a suitable metric for describing complexity. First of all, it never gets very big. And second of all, we expect the complexity metric to be quite far from left invariant and be right invariant. Okay, so that brings us then to something I mentioned last time, a theorem. You can find it in a paper by Milner, mathematician Milner. He didn't invent it, he didn't discover it. It's a very rich literature on these kind of metrics, and the Russian mathematician Arnold wrote some very, very beautiful papers on it, connecting it to, of all things, fluid dynamics. Ocean of fluids is governed by these kind of actions. But as I said, there's a whole literature. The only part of it I can understand was written by Russian mathematicians. Why is it so easy to understand Russian mathematicians and so hard to understand any others? Does anybody else have that? No.
No,
Really? Oh.
I have never heard anyone express that sentiment in any form before.
Wow, this is so clear. And Kolmogorov and these people, this is so
Color
clear.
is pretty clear.
Maybe we've just
Sinai is very clear. And,
maybe we've just been reading different Russian mathematicians, but
oh, you read Russian mathematicians whose name either begins with Schwartz or with G, Gelfand. They're a little harder, but not that hard.
I only read geometry papers, they're incomprehensible.
Okay. All right, so the most general, this is a statement about the most general right invariant metric. So in that sense, it's a very wide class of metrics which includes any kind of thing that we would be likely to call a complexity metric. dl squared, I know I said it last time, but let me do it again. d omega I, d omega j. I and j now, again, mean these directions in the Pauli space, very high dimensional, 4 to the n, and then a kind of a tensor in the ij space. How big is that tensor? How many components does it have? It has 4 to the n times 4 to the n components. It's a very big tensor in general. This is the metric where this object, the omega, let me write it down lower, the omega I differential is equal by definition to I trace of, do I have this right? D U dagger. I actually wrote it down correctly. Yeah, I did. The I is I trace U dagger. So far, so good. Sigma I, and then U. Incidentally, it can be written in terms of using various complex conjugates and hermitsicity tricks and so forth. This can also be written in terms of U dagger and DU. The trick for it. It's true. In fact, I think this thing is Hermitian. This is Hermitian, I think. Exercise for the reader. Rewrite this in terms of differentials of U and U dagger. I'll let you do that. Okay, so this is what goes in here. If I was interested in the action of a particle moving on this geometry, I would replace this by what we call U dot and U dot, and then integrate it over time. I won't do that at this point yet. But this would define an action for a particle moving on a complexity geometry. In other words, a possible action to describe the motion of a state vector, except in this complexity geometry, we're not changing the, okay, we'll come back to it soon. So this is a metric which is of a very general form. Where was the simple case? The bi-invariant metric, which was just trace of U dagger dot, or du dagger du. This is another exercise. This object here involves the product of two traces with a matrix in between. If capital I or script I, ij here is proportional to the Kronecker delta, there's the Kronecker delta, then you can simplify this and it just becomes this. It becomes a single trace, and it takes a little bit of thought how to rewrite it, but you can rewrite it.
Does it have to be like strictly proportional to the delta matrix or just like diagonal?
No, it has to be strictly proportional to it. We're going to take these i's to be diagonal,
That's why.
but not proportional to the unit matrix. All right, now, what Nielsen says is he says if you want to represent complexity as distance between unitary operators with a metric of this type over here, let's suppose we're at some point, and at that point passes a bunch of tangent vectors. The tangent vectors are associated with these ij directions, the Pauli directions. In other words, a tangent vector starting at this point would be to take this unitary vector here, operator here, and multiply it from the left by a little e to the I times a sigma, and displace it a little bit along the sigma I direction. That would correspond to some local coordinate patch near the tangent point here. And what we would want to do is we would want to punish, let me call it punish or penalize directions which themselves have very high complexity, and that would mean large weight. If we're interested in a k-local situation, we would want to say that anything which is not k-local, a Hamiltonian, for example, which is 7 local instead of 2 local in a world where we're interested in 2 local things, we would want to punish it heavily and say, roughly speaking, we're not allowed to move in that direction, or at least make it hard to move in that direction. And that would mean making the metric, the components of the metric along that direction large. All of the k-local directions, two Pauli operators, 1 Pauli operator for 2 local system, we would not want to punish in that way. And so we might say then that these I coefficients should be set equal to 1 as long as I and j have weight less than or equal to k, little k, and then for them to be big. Nielsen says very big in all directions which are not k-local directions. Yeah.
I guess they're just sort of exponentially more complex directions, right?
Very
So
definitely.
even if it's
exponentially.
heavily penalized, there's still a sort
That's
of,
right.
the probabilities kind of add up, right?
That's true.
Is that why you need an exponential suppression? Or how do you pick
Well,
it?
no, it's not because of, no. Well, ultimately, of course, it does come down to the simple fact that n's large, and so, but here's what's being reflected. Let's take the distance between any 2 points measured with this metric here. The first thing I could do is calculate the distance with bi-invariant metric. Let me start with that. With the bi-invariant metric, the metric distance is not going to be large. It will never be larger than pi over 2. Okay. What's the maximum? Go along this same exact curve here, the geodesic as defined by the bi-invariant metric, and calculate its length in the right invariant metric here. Well, it will be no bigger than the maximum I here. Can you see that? Let's suppose the maximum I, you should,
Right.
yeah, it can't be bigger than the maximum weighting
Pi over 2 or something.
times pi over 2. Right. If we know independently that the maximal complexity of any relative complexity of any points is, let's say, 4 to the n, which we do know purely on complexity grounds, 4 to the k, 4 to the n, that there are pairs of points whose relative complexity, number of gates that it would take from one to the other, is of order 4 to the n, then we must have that the maximum I must be of order 4 to the n. Okay. This was Nielsen's logic in choosing the weighting factors. Here was his choice of weighting factors. For all I and j whose weight is less than little k, choose it to be 1. You can easily move in those directions. And for all I and j which are weight larger than k, choose it to be humongous. And then you'll be restricting yourself to motions which, except at enormously large cost, will have to be along the easy directions, let's call it. That is okay for some purposes, but it fails to reproduce things that we do know about complexity, in particular the switchback effect. It's too severe. It just punishes too heavily things of relatively low complexity. For example, it would not punish 1 and 2 qubit operators, and then would completely punish 3 qubit operators just as badly as it punished n qubit operators. It's too severe. The word is draconian. It's too draconian and punishes too heavily to reflect properties that we do want to reflect, properties that we know about black holes and properties that we know about circuits. There is another choice which goes like this. Let's assume that a operator of weight W has a complexity or would pay a penalty for it, which depends only on the weight and not on the total number of qubits. For example, we'll say that 3-qubit operators are 3/2 times, or maybe 10 times, or 4 times, whatever, more complex than 2-qubit operators. And 5-qubit operators are even more complex, but only dependent on the 4 and the 5, or the 3 and the 4 and the 5. In other words, our definition of complexity or weighting factor or penalty for a gate or a term in the Hamiltonian will depend only on the weight of that and not on the total number of qubits. Take a computer which has 100 qubits versus 1,000 qubits. The assumption is we pay the same price for a 10-qubit operator in either case. That's different than Nielsen's definition. Okay, so but still, we still require the largest value of I to be 4 to the in order that the maximally complex states have complexity of order 4 to the n. There's only one way to do that, and that's to take the coefficients of the I here, of I. I'm assuming it's now diagonal, to be of order 4 to the weight. The maximum weight is incidentally equal to the number of qubits in the system. So for maximal weight, namely of order n, we're taking I, the eigenvalues of I, to be of order 4 to the w, 4 to the weight, or 4 to the n, but we're turning it on more smoothly as a function of w. We also don't want to turn it on until we get to w equals little k. We want to allow everything of up to k qubits and then start punishing it. And so a simple answer would be 4 to the w minus k for w bigger than k, and just 1 for w less than k. But nothing is terribly critical about this. Just we want a slow turn or a continuous turn on that doesn't radically just come in and suddenly punish things of weight 3 but not 2. Turn it on smoothly in such a way that the first k weights are unpunished. That's a very different way to penalize the high complexity operators, and it does work much better in reflecting the properties of ordinary circuits, and reflecting the properties, also the properties of black holes. When I say reflecting the properties of black holes, we can either use action or volume to calculate the complexity of switchback operators, just the growing complexity, and we will not get the sort of answers that Nielsen would get.
Does it even matter that you separate out the first k?
It probably doesn't even matter that you separate out the first k. It probably doesn't even, I don't think it does matter. Yeah. Well, I would say, for example, if you're doing S1K or something like that, and you're going to some large Q limit, meaning little k being large, I think you would want to separate out the first Q and say those are easy, and then start it from there. Right. Okay. So. Okay, so that's a setup. We now have a definite metric. Metric precisely. Delta ij, if the weight of I is less than or equal to k, and ij, for example, equals 2 or 4 to the w minus k. Sorry, it should be for wi less, for w, or what is it? Yes, wi less than, yeah,
it's
the wi larger than k. Yeah, okay, so things get more gradually punished rather than just whacked when they're bigger than 3, let's say.
Richard?
Okay, now, what do we want to do? We want to understand this geometry, and we want to understand motion on this geometry. One of the interesting questions will be, is motion on this geometry chaotic? Now, I can tell you right now, the motion on the bi-invariant metric is not chaotic. It is not chaotic, and in fact, if you take the bi-invariant metric and you start out at a point, and you shoot 2 geodesics, instead of those geodesics diverging, geodesic, what's it called, geodesic deviation, they will converge.
Well, they'll converge after a little bit of time.
Yeah, sure.
Won't they initially start diverging?
It doesn't, when I say divergent, I mean that they're not gonna, their geodesic deviation, yes, they'll start diverging,
Yeah.
but the second derivative will be,
Okay.
yeah. They won't do that.
The space
They'll
is
do that.
positively curved.
Positive, yeah, that's right. The space is positively curved. They won't, the distance between them will not grow exponentially, okay, on this geometry. So it's not a good measure of chaos or growth of operators or any of those kind of things.
Is there some interpretation for this metric, other than complexity?
It measures the degree of orthogonality of things. So, if we were thinking about states instead of unitary operators, taking 1,000 qubits and just flipping one of them over is as far away as doing something incredibly complicated and leading to a wildly complex state. Would be no further away, it might even be less far away.
Yeah.
So this is the usual measure that we use in quantum mechanics to represent things like interference and so forth. It's just the wrong thing for describing complexity and for chaos, I think. Yeah.
What happens if you consider sort of off-diagonal pieces in your metric?
I don't know, we never studied it very much. It's a good question, and I don't know. I don't have an answer. All right, so how would we tell? Oh, the question of whether the motion is chaotic, which means positive Lyapunov exponents, has to do with the way the distance grows between these points. The distance depends on what metric we use. So it will not be invariant under a change of the metric. It'll be invariant under a Hamiltonian transformation, but it won't be invariant if I just go and slap a different metric on the geometry. And in particular, if I slap a metric on which I intend to be good for studying complexity, it should have the effect of making these geodesics diverge. The point is here, well, first of all, let's go back. Let me just go forward, plow ahead, and then define things more carefully. All right, so with an appropriate definition of the metric, it may be that we do have this kind of geodesic deviation that leads to positive Lyapunov exponents, and with another definition of the metric, we may not. So, what do we do to look for the chaotic type of behavior versus the non-chaotic behavior? Anybody got a suggestion?
Keep the curvature.
The curvature. We have a metric, we compute the curvature. If we get positive curvature, we go hang up our chalk and say we did something bad. If we get negative curvature, that means that that states are going to deviate away from each other in the way that you might expect for complexity. I'm not going to go through the whole derivation of the curvature. And in fact, what we're going to do is calculate the curvature, the sectional curvature, so-called sectional curvature of a generic section. Now what a section means, mathematically what I mean by section and sectional curvature, is you take two directions, two geodesics intersecting at a point. And you consider, or you take, let me define it in terms of Hamiltonians. You generate motions by u dot is equal to hu. You take two different Hamiltonians and you consider all linear combinations of them. All linear combinations, one I'll call h, the other I'll call delta. I don't remember where this, and now consider all linear combinations of h and delta and take the space swept out by the geodesics determined by those linear combinations. Those will form a two-dimensional surface. Okay? The two-dimensional surface, there will be a point at the center, the geodesics radiate away from there. Each one of these geodesics is associated with a particular combination of h and delta, a two-dimensional surface, and then look at the curvature at the point where all these geodesics intersect. That's called the sectional curvature, and it is a measure of how these geodesics diverge from this point here. We'd like to do better, we'd like to follow it for a ways, and we actually don't know how to do it, but we do know how to calculate the standard sectional
I
curvature.
mean, the curvature of the induced metric.
What's that?
I mean, the curvature of the induced metric.
Yeah, absolutely. That's right.
No, but, sorry, isn't
The curvature of the induced metric, yes.
Okay, I thought that was, isn't it this sectional curvature like the Riemann away from that point?
Say it again.
I mean, the induced, so is it an induced curvature or is it an extrinsic, more extrinsic curvature?
Yeah, there's the projection of the curvature versus
But I think this is kind of the Riemann in this direction, right? Or,
Yeah.
So it's not completely induced curvature.
Yeah, there's two different, not necessarily which one's which, but you're saying it's a projection.
I think you need the Riemann in the normal directions to this geodesic.
It's tricky, I don't remember the exact definition in terms of the Riemann, but it is the induced curvature in this, in the two-dimensional surface.
Is it the curvature on the induced metric on the 2D surface?
Yeah.
That's different.
That's
than what you're
different
saying.
than what
Than what?
they were talking about. There's
I know.
two things you could do. You could compute Riemann in the ambient
No,
space and project it.
No, if you know Riemann,
But you're just,
if you know Riemann, you can compute this. But in fact, here's what's true.
so you can't just compute, no.
No, it's not just the components of the Riemann tensor in those directions, it's not. But here is what is true. If you take all possible planes like this, with an appropriate measure of planes and different orientations, then the average of the sectional curvature is the scalar curvature of the space. Yeah, that is true. Okay.
Can you not just compute the Ricci scalar of the metric?
That will give you the average curvature averaged over all these sections. You
But
can.
presumably the sign of that should be enough to tell you,
Well, the sign of the full curvature just tells you that it's in some directions it's deviated.
Yeah.
Maybe some don't.
Yeah. That looks, I think that's a little harder than just calculating the two-dimensional curvature. It's probably not much harder. And I'm not gonna do the computation here, so don't worry. But I'll tell you what goes into it. And there's some nice physics and definitions and things that occur in other places, which it's kind of fun to see the connection between them. Okay, so here's where we are. we have a point that I'll call t equals 0. And then we have two geodesics associated with, one of them is associated with the Hamiltonian h, and the other is associated with the Hamiltonian h plus delta times d theta. D theta is just a small parameter. Delta, it was not chosen to mean small. This was just another Hamiltonian. H and delta, I didn't want to write H1 and H2 because there's more indices, and so we just said, let's call it H and delta, and I don't remember why. I remember why. We first called it H and K, but then we had used K so many times already. Okay, let's find the Greek letter to call it. And I didn't know a Greek H. Is there a Greek H?
Isn't Ada Greek H?
Oh, I didn't like Ada. We want to capital, first of all. And that would just make it H again, I think. I don't know what it would be. And we didn't know the Greek alphabet well enough, so we said delta. These are two Hamiltonians. These are two Hamiltonians. And let's follow this geodesic out, e to the minus I h t. T is just a parameter along the trajectory. And this one parameterizes e to the minus I h plus delta d theta t. We go out a certain distance, a certain t, and now we look at the curve or the trajectory, the shortest curve between those two points. And we're going to calculate basically the geodesic distance between those to leading order in theta, in other words, to just d theta, and as a power series in t. That's enough to calculate the g theta theta component of the metric, and the GTT component of the metric we can also compute. But basically, this interval over here, what is this interval? This interval is what happens if you proceed, well, let's say, backward along here and then forward along here. In other words, this interval is a differential of a unitary operator, a small unitary operator, so to speak, or a small deviation from a unitary operator. And that unitary operator is, let's call it, which way to define, e to the minus I h t, e to the minus I h plus delta d theta. You go one way, and then you go the other way. Oh, one of them is plus. One of them is plus. You go, if delta was 0, or d theta was 0, then you would just go out and come back to the same place, and you come back just to the same place. If there's a small difference in the Hamiltonians, then you come to a different place. This physical operation of running a system with a Hamiltonian and then changing the Hamiltonian a little bit, perhaps not even on purpose, and then running forward with the new Hamiltonian, is called a Low-Schmidt echo. It's a thing experimentalists do, look at nuclear magnetic resonance, you do things like this. And
But that Low-Schmidt echo is the expectation value of this, right?
yeah, but yeah, the process itself I would call a Low-Schmidt echo. Yeah, and the expectation value of it is related to the theta theta component of the metric in here. All right, so this is just an exercise in computing, as we said, various kinds of expectation values, or in this case, traces of Low-Schmidt operators. The question is, where does the particular metric come in? And I'll tell you in a moment. All right, so we have this Low-Schmidt operator. I'll call it e to the lambda. Lambda is for Low-Schmidt. And it's lambda, really, that we want to calculate. It's lambda, which is a measure of the deviation along here. And what's the trick for calculating the Low-Schmidt operator?
CBH. Campbell-Baker-Hausdorff.
Yeah, Campbell-Baker-Hausdorff, of course. Right, we just use the Campbell-Baker-Hausdorff lemma. Unravel this. Get a few terms, however, we expand it to power d theta, to linear order in d theta to get the metric, and to whatever power in t we want to keep to see how far we go. And that will basically give us the theta component of the metric in here. Right? The radial component of the metric can also be easily computed. It's just represented by an expectation value of h squared. It's just an expectation value of Hamiltonian squared. Gives you the component of the metric this way. The component of the metric this way comes from the Loschmidt calculation. And the calculation is straightforward. There's only one point. All right. Yeah, no, it's almost straightforward, but let me tell you where the penalty factor comes in. In calculating, for example, the theta component of the metric, we will have to calculate trace of lambda, which is this Loschmidt operator here, which you get from Campbell-Baker-Hausdorff, dot lambda. Okay, what do I mean by dot lambda? Lambda is itself something that can be expanded, lambda I, sigma I. Sigma i's represent directions, the directions in the tangent space at this point. You can expand this operator, it's a Hermitian operator. You can expand it in terms of the sigma I. And then, once you have it expanded in terms of sigma I, the dot product here means contracting it with the penalty factor I. Calculating the trace of this would give you the theta component of the metric, the induced metric induced from the complexity geometry. So this is where the particular penalty factors come in. One more thing, how does it depend on the particular Hamiltonians that we've chosen here, H and delta? Well, it does involve them, and you have to calculate averages over the ensemble of Hamiltonians that you're computing. I'm assuming now that we're going to average this over the ensemble of Hamiltonians. In other words, we have H being given by some sum J times sigma. We have delta being given by some other sum, let's call it D times sigma. These are statistically distributed, let's say, according to Gaussians and so forth and so on. At some point, we will have to calculate averages or ensemble averages over these coefficients, delta and D, but that's very easy. That's very easy. And you get an answer. You get an answer which is...
What is the difference between J and D from the point of view of the ensemble?
Just taking two ensembles. They could be the same ensemble, but two ensembles. Just the experimenter decides to pick H from one ensemble and delta from another ensemble. A special case of that would be the same ensemble. Okay, I'm going to write down the answer for the ensemble averaged curvature. It turns out not even to depend on the ensemble as long as the particular instance is generic. And what you get is the sectional curvature at t equals 0 is equal to 2 to the 8th. I don't know where that came from. Divided by k or n. In other words, as the number of qubits gets big, the curvature goes down, and then there's a factor of 1/3 minus I3. I'll tell you what I3 is in a moment. I'll tell you the generalization of it over 4. Now, I'm assuming the two local Hamiltonians. I3 is the first penalty factor, which is not equal to 1. It's presumably bigger than 1.
just equal to 4?
Yeah, something, right.
Okay.
With that, yeah. But I'm not particularly fixing it with any precision at this point. Yes, it's, according to my notation before, it would be 4. Okay. In general, there's a more general formula. The more general formula, I think, is the same thing, 1/3 minus the first non-trivial penalty factor. If we're talking about SYK with 4 local operators, I think this would be I5, or maybe I6 in that case, because I think you don't want to have odd numbers in the Hamiltonian. And we calculated it for a number of different kinds of systems, SYK for just Pauli operators and so forth. Incidentally, Michael Nielsen also calculated it, got the same answer, but it was buried somewhere in a morass of notation and confusion that we could not sort out, so we calculated it ourselves. Nielsen was kind of an interesting case. He was a quantum computer scientist. He had a physics background, but his main background was in computer science. And he knew nothing about general relativity, and nothing about differential geometry. He was very good at arithmetic, but had this idea to use differential geometry to explore. So he had to go learn differential geometry, and he must have read the wrong book. I don't know what book he read, but whatever the hell the notation was, it was abstract cockamamie notation, which was, and he wrote the paper in that notation. It was very hard to read, whereas this calculation was rather easy. I think you eventually penetrated his notation. You didn't. But, okay. But the calculation is really quite easy. And this is the answer that you get. So in particular, if I3 is sufficiently big, but fixed, not 4 to the n. Oh, in Nielsen's case, I3 was 4 to the n. Yeah, the humongously big curvature. His whole space had a curvature, a radius of curvature which was tiny, tiny, tiny. But with a more modest, less draconian penalty, let's say I3 equals to 4, for example, the curvature comes out negative, and it comes out to be of order 1 over the number of qubits. It sounds like a very small curvature. Go ahead.
So do the other coefficients just not appear, or are they just suppressed, or?
At this order. At this order. At this order. You see what happens
Okay.
is, yeah. The calculation here picks up the first commutator.
Yeah,
between
exactly.
here and
So you'll
here.
generate
Yeah,
higher and
that's
higher
right,
order.
that's
Yeah.
right. Calculating the next orders is complicated because the surface defined as I defined it, all right, I defined it by passing geodesics through here. It turns out the surface has a substantial extrinsic curvature. The meaning of having an extrinsic curvature is the statement that the actual geodesic between these 2 points doesn't stay on the surface. So if you actually want to calculate the distance between geodesics between here and here, you have to move off the surface a little bit, and this looks hard. We have not figured this out. Somebody wants to be interested in this. It's a very interesting geometry problem that we would like to know the answer to calculate the higher orders in T. In other words, to move away from the tangent plane itself. But what we know is that for I3 bigger than 4/3, the curvature is negative, and most important, it's of order 1 over k. That sounds very, very small. It sounds like it might just be totally uninteresting in the case of k equals very large. But it turns out this is exactly what you need, order 1 over k, to get the right Lyapunov exponent to describe the chaos effect. It's exactly what you need. So that wasn't put in, it's an output. And I'll show you next time how it works, why the curvature of order 1 over k is the right thing. Is the right thing in particular to describe the switchback effect, you can call it, or you can call it the Lyapunov exponent, you can call it the scrambling effect, and this is reproduced by a curvature this big.
So this 1 over k is independent of the main entry, more or less. As long as,
Independent of the what?
of the metric, as long as it's diagonal, you always have this 1/k.
Well, yes, yeah, that's right, that's right. That's right, as long as the coefficients of I are independent of total n,
Yeah.
then you'll get this 1/k. So, in Nielsen's case, you'll get this enormously big curvature. Let me tell you what a very, very big curvature does. If you ask for, that effectively means that the theta component of the metric is very, very large. Okay. What it says is if you want to find the geodesic between here and here, the most favorable strategy, if the curvature were infinite, the most favorable strategy would go all the ways back to here and then go to here. That would be the shortest geodesic if the space. Basically, the answer is you go back until you get within a radius of curvature, and then you go forward. If the radius of curvature is very, very large, you go all the ways back and then forward. That's exactly destroying the switchback effect. The switchback effect says, it says what it says. You say you go back a certain distance and then you go back to scrambling time. If you insert the scrambling time, then what it requires in order that the geodesic reproduce the correct scrambling effect is a curvature of order 1/k. So we'll show that next time. I'll show you how that works. And what do we want to do next time?
So, I've harassed people.
I had proposed to just finish up this and then,
I have some stuff I could talk about, but next week is completely insane for me.
Okay,
Okay.
then how about the week after that, next week?
That would be great.
all right, good. What are you going to